All right, let's dive right in. Today, we're talking about high-temperature PEM fuel cells. And trust me, this isn't just a story about engineering. It's really about a technology that comes along, solves a ton of old problems, and in the process, creates a whole new set of fascinating challenges. So I want you to keep this question in mind as we go. What if a fuel cell's biggest weakness was actually its greatest strength? Because the one thing that used to plague these designs, heat, has been completely turned on its head. It's now the secret sauce. But, as we're about to see, that strength, it definitely comes with a price.
So what's the big deal with temperature anyway? Well, on the left, you've got your standard low-temp fuel cells. They run cool, below 80 degrees Celsius, but they are incredibly picky. They get poisoned by the tiniest fuel impurities, and they need this whole complicated system just to manage water. Now look at the right. That's our high-temp hero. By cranking the heat up to between 120 and 200 degrees, the whole system gets simpler, tougher, and, this is the big one, way more tolerant of the kind of real-world, slightly dirty fuel we'd actually want to use.
To really get why this is such a breakthrough, we have to look at the problems it was built to solve. So let's start with Section 1, the fuel cell's fever, and the limits of running cool.
And look, the promise here is just massive. This quote really gets to the heart of it. PEM fuel cells aren't some niche little technology. People see them as a potential cornerstone for our entire energy future. So yeah, the stakes for getting this right are about as high as they get. But here's the catch with those conventional cells. They have some really serious flaws. I mean, look at this. Their sensitivity to carbon monoxide is just off the charts. A tiny amount, we're talking parts per million, can absolutely cripple the cell's performance. That means you have to feed it ultra-pure, super expensive hydrogen. And on top of that, they need water to work, which creates this delicate dance. Not enough water, the membrane dries out and fails. Too much, it floods. It's a complicated, expensive mess that's held this tech back for a long, long time. And that brings us right to the solution. Welcome to Section 2, a high-temperature hero, and the pretty ingenious material that makes this whole thing work. The solution, it turns out, was kind of elegant in its simplicity. Just turn up the heat. If you run the fuel cell hotter than the boiling point of water, all those tricky water management problems, they just poof, go away. And it gets even better. That heat makes the catalyst way more resistant to getting poisoned. At these higher temps, impurities like carbon monoxide just can't stick to the platinum catalyst as easily, which keeps everything running clean and smooth. So what's the magic ingredient that lets you do this? It's a polymer called polybenzimidazolol, or PBI for short. It was first tried out for this back in 1995, and it's the tough, heat-resistant backbone that can take the brutal conditions inside one of these high-temp fuel cells. So, how does it actually work? Well, the easiest way to think about it is that the PBI membrane is like a high-tech sponge. Its whole job is to just soak up and hold on tight to phosphoric acid. And that acid becomes the new proton highway, doing the exact same job that water did in the old low-temp cells. It's a brilliant swap that lets the fuel cell run completely dry. And this chart just shows you how incredibly tough this PBI stuff is. Its glass transition temperature, that's basically the point where it starts to get soft and lose its structure, is way, way up at 430 degrees Celsius. So operating at a typical 160 degrees, that's nothing. It gives it this huge safety margin at a temperature that would literally melt the older membranes. So, okay, what does this all mean in the real world? Well, since it can handle impurities, you can use cheaper hydrogen made from things like natural gas or methanol. The whole system gets simpler and cheaper because you can throw out all that water management gear. And as a really cool bonus, the waste heat it produces is actually hot enough to be useful, perfect for generating electricity and heating a building at the same time. It's a win-win-win. But, like I said at the beginning, every solution has its own problems. And that brings us to Section 3, the price of heat. Because here's the thing, the very heat that solves so many of our problems introduces a brand new enemy, decay. At these temperatures, everything is more stressed out chemically and mechanically, and things just wear out a lot faster. Researchers have basically identified what you could call the 4 horsemen of high-temp fuel cell death. You've got the membrane itself breaking down, the precious catalyst degrading, the carbon that holds the catalyst corroding away, and that vital phosphoric acid just slowly disappearing from the system. And each one of these is its own complex headache. The membrane gets attacked by nasty chemicals and can literally get thinner over time. The tiny platinum catalyst particles can dissolve and then clump together, making them less effective. The carbon support can just corrode into nothing. And that phosphoric acid, our essential proton highway, can slowly evaporate or get washed away, basically starving the cell. So how do you fight these invisible enemies?
Well, scientists use what are called accelerated stress tests. Basically, instead of waiting 5 years to see what fails, they torture the cells to speed up the aging process. They'll rapidly cycle the temperature from hot to cold over and over. They'll slam the electrical load up and down. They'll even deliberately starve the cell of fuel, all just to see what part breaks first. It's a critical tool in this race to make them last.
Okay, so we've got this amazing technology, but it's constantly trying to tear itself apart. How do we fix it? That brings us to our final section, the road to reality.
The strategy to make these things last really comes down to a three-pronged attack. First, you just engineer better, tougher materials, like creating new PBI membranes that are stronger and better at holding on to that asset. Second, you operate the system smarter, with control software that knows how to avoid the most damaging conditions. And third, you build in real-time diagnostics that can spot a tiny problem before it becomes a major failure.
So where are you actually going to see this stuff pop up? Well, combined heat and power for buildings is a huge one. But also think about backup power for things like cell towers or auxiliary power units on long-haul trucks so they don't have to idle their big diesel engines. They could even be used as range extenders for electric cars with a little methanol-powered fuel cell that kicks in to charge the battery while you drive.
The magic number, the one everyone is chasing, is 50,000 hours. To put that in perspective, that's nearly 6 years of running nonstop. If researchers can hit that target by getting a handle on all these degradation issues, this technology becomes a real commercially viable option for stationary power, and that changes everything. And this is where it gets really interesting, because it all plugs into a much bigger vision. Since these fuel cells are happy to run on methanol, which is a liquid fuel that's easy to handle and can even be made from renewable sources, they become a key piece of the puzzle for something called the methanol economy. And that brings us back to where we started, with a question. This technology is a huge leap forward, turning heat from a liability into a superpower. But the price for that power is this constant, relentless battle against decay. Whether we can win that battle and unlock a future powered by clean, liquid fuels like methanol, well, that's the question that scientists and engineers are working flat out to answer right now. Thanks so much for joining me.